Now we'll move into section 11.9, where we will discuss how to represent functions as a power series. But just before we jump in and do that, let's just take 1 second to think about 11.8. 11.8 really contained a lot of information, just jumping into this idea of power series, and to realize, right, power series, they're just called that because they have the variable x raised to a power. So there's nothing clever to the name there, but we really introduced a lot. What is a power series? A basic understanding of how a power series can be a function. Just the idea you have the variable x, so replacing the variable x as your input and whatever that sum is, that is your output. So again, we really established a lot of ideas, but if you're a little lost going through all of that, realize for 11.8, the biggest thing is the intervals of convergence. So at somewhere around the 40-minute mark, I think at about the 37-minute mark in the 11.8 video, I do a few problems discussing the center of a power series, but really the problems right after that, finding the intervals of convergence. That's the biggest thing to get used to in that section, that you are given a power series in the first place, and then mostly through ratio and root tests, using those to determine for what values of x those series converge. And again, the three possibilities, they never diverge entirely. It either converges at a minimum at its center, or some interval away from its center, or for the entire x-axis for all values of x. Those are the three possibilities. Now, we also mentioned ratio and root test, very, very common for those, but you'll notice even as we start working in 11.9, if we're lucky enough to recognize it's a geometric series, we can make that process a little bit easier. Okay, so that's what we did in 11.8, focusing on what is a power series in the first place, and then thinking about what are the x's that it will converge. So now we make that next big step. How can we have a regular function but can write it as a power series? And we start with a very simple example. If I have the function f of x is 1 over 1 minus x. This is a regular function as an equation that we're very much accustomed to, but this can be easily conformed into a power series. And the way to do this is based off of this exact form. That this function, and that's the key to these first several problems, these functions all have this same similar form, and that the function can be written, can be re-understood, sometimes some slight algebraic manipulations, and can be written as the sum of a geometric series. So we will find functions of this form, and then we will write them as AR to the n. Now that's the one little change, well, the second little change. We've already used that as a sum of a geometric series, but we used to call it A was always the first term, R to the n minus 1 power, but that's when we started at n equals 1. Now with n equals 0, notice with that starting point, it still works out the same way. If n is 0, you get AR to the 0, which is A. When n is 1, you get AR to the first power. N is 2, you get AR squared, and so on. So even though we have that slight change that we're starting now, our counting variable starts at 0 instead of 1, that makes that little change here. The exponent is n instead of n minus 1. But that's going to be our main key. That right off the bat, I look at this, I could see that A would be 1, and that R would be my variable x, and that this function, this is the same f of x, this could be represented as 1 x to the n power. And 1 times that is just the x to the n. So that is our first example. There is a regular function written with a normal equation, and through this connection, we can see that that same function, I'm not changing my notation here, it is the exact same function f, can be re-understood as this power series. So that this and this are exactly the same. But now there's one other little extra catch. This is the idea of a representation. These represent the same function, but only where this power series converges. That's the extra catch. Up here, the only problem with this function would be x is 1. 1 would be the only thing not in the domain, because that would make the denominator 0. But for this power series, the power series has to converge. And in our geometric series, we know that only happens when the absolute value of r is less than 1. Well, that would be translated in this problem to the absolute value of x is less than 1. So this would be the interval of convergence for this power series. So that means only for these x values would this function with this equation and this same function with the power series representation, they would have the same value. And we could go through and prove that, but it's just running around in circles. If x is 1/2, you'd look at that as a geometric series, you'd use this sum formula, and you'd find out the final sum. If you used x as 1/2, you'd end up getting 1 over 1 minus 1/2, you'd get 2. So that would be the same value. But if you tried plugging in x as 2, that works just fine here. But when you plug x as 2 in here, it's tempting to just try and plug it into the sum formula, but you would not have a convergent series. So some people would look at that and say, okay, well, this function is the same as this, but it only works for these x's. Isn't that limiting? It is, but here's the last little catch. We're not going to do too much of this. As we do these, this is a power series centered at 0. And that was when we first wrote out our power series. We started with just the generic x's, and then we quickly pointed out that we should really fully consider x minus a, with the center value being a. But if it's just the x to a power, we could think of that as x minus 0 to the n. So I don't want to use a here again. We're using a for the first term in a power series, in a geometric series. So I don't want to use that same variable a again. But just to realize that is the same as that. The center is 0. If you needed this to work for other x's, you could play games with the center. So you could try and make sure that this is centered at 2 or at 3. And I'll show you a little bit of that, but that's not our real concern. So that is a good point. For those of you who may have thought, isn't that limiting? It is, but we could change the power series if we needed it to work for a different value of x. So that's still just the first problem. But that gives us a very good guide for where we go from here. So for the following problems, we are going to find power series representations for the following functions. Examples 1, 2, and 3 in your book are all very similar to what we're about to do here. So let's look at problem number 1. Let's look at, we'll keep this one simple. That's a of x. This is just going to be one tiny little change from our first problem, our first example, to the first full problem we do. So, point here is just not everything is going to be so completely perfect the way this one was. That when we say we want this to have form a over 1 minus r, we have a lot of freedom to manipulate, but what do we need at the end? We need to identify what is the a, what is r, and this has to be a 1 minus. Well, I already have the 1, but how can a plus x be written as minus r? Well, that's not that bad. We'll just write it as minus a minus. 1 over 1 minus a minus x. Now we've made that little transformation. So now when I plug in, a is 1, r would be minus x to a power. And there is our power series representation. That's really all there is to it. Now, the one tiny little thing that does come next, though, when you have this is a perfectly good power series, and just most of the problems here, they ask for the power series, and they follow up, also find the interval of convergence. I could do that the long way. This is where in 11.8, you are given this as a power series, and you could go straight to your testing. But here we added a new first step. First, you had to get this power series. But here's the little advantage. Don't take this from scratch. Take advantage that you know you are using that this is the sum of a geometric series. So just like up here, just go right to R. Don't go through and do a whole ratio test on this. Especially the ratio test, that's where, or root, that's where sometimes we have to do that extra work with the endpoints. That's a little bit of a pain. But for right here, just like we did here, absolute value of R has to be less than 1, and the absolute value of negative x is the same as the absolute value of x. We end up with the exact same interval of convergence. So that would be it. But now, coming back to this. So we've solved everything. They asked for the power series, there it is. I then snuck in this second question, find the interval of convergence. We did that as well. But I just want to point out one little thing. When we had power series, we kind of talked about having that c sub n term and then the x minus a to the n power. That's still important. The book still likes to break these apart, so it still has that same similar form. Now, that's not going to make total sense why we're doing it now, but by the end of this video, you'll start to see why we do that. So this is a perfectly good answer. You give this on a test or a quiz or your final exam, you would get full credit. But in the back of the book, they would do that. That's the only little extra catch. They would do that. And all we did was just distribute that exponent. This is minus 1 times x. They're being multiplied to the n power, so I do get to distribute the exponent. And this is exactly what I was just talking about a moment ago. Now, there's your x minus a to the n, so there's your real power series component, specifically one centered at 0, which again will be very common. And then here is the coefficient part. So you could still write out terms. This happens to alternate. That's not the point. It, again, was just to break this apart, to have those components separated. Coefficient and then variable. Okay, so not so bad in problem number 1, hopefully. Let's do 2 more of these. And let's just slowly bring them along a little bit. Number 2, let's take a look at something like x cubed over 10 minus x. Actually, let's even make this 100 x cubed over 10 minus x. Now we're, some people want to already make the jump, say a is 100x cubed. Well, one quick thing to realize here, a does not just have to be a number. A can definitely contain a variable as well. But the issue, this is not a because this is not 1. Once you make this a 1, then we could start talking about what is r, what is a. But don't say this is a and this is r. The first thing you have to do is make it match this form. That's what we did here. All it was here was just play a little game, change that plus to a minus. But here, this needs to be a 1. How do I make that a 1? Well, I factor out a 10. That's it. Now, that 10 would simplify here. This would end up being a 10x cubed after those cancel. And now we have that perfect form. A, all this is canceled, a over 1 minus r. So this would become the series a 10x cubed times r x over 10 to the n power. And once again, that's it. That is my power series, but just like I did up here, I'm going to come back and just clean that form up just a little bit. But just before I do, let's finish up the interval of convergence. And I know some people, why not just clean it up right here? I'm just pointing out that this is a correct answer. This does satisfy the answer. But like I keep suggesting, and it's happened a lot throughout Calc 2, the book is not going to write that. The book is going to clean this answer up a little bit. So I don't mind if you leave it that way, but you should be able to realize when you look at the book's answer how you would make the connection between the two. So, but that's a good answer for now. The interval of convergence. Again, don't go through and do a whole power series on this. Just like this one, all these first couple of problems we're doing with this, they're all based on the sum of a geometric series. So once again, it's just about the absolute value of r being less than 1. This one will become the absolute value of x is less than 10. So our interval of convergence would be negative 10 to 10. And one more time, I know I keep repeating myself, but these are difficult units as we finish the class. So I really want it to be clear at every step. Because we used the geometric series, that's why we knew we didn't have to test the endpoints. If you did this with a ratio test, it certainly would have been more work, and you would have ended up with this has to be less than 1, but then technically you would have to check what happens when x is negative 10 and positive 10, because in a ratio test, you don't know what happens. You don't know convergence, divergence when L equals 1. But for geometric series, we know it has to be a straight less than 1, so we're done right here. Okay, and now just come back up here and finish this. This becomes x to the n over 10 to the n. Here's the subtle little manipulations. Some people, after you distribute that, and this one, that was literally all I can do. But then after that, the next thing would be combine stuff you can. So definitely the book would combine those x's and say that is x to the n plus 3 power. But now where do the 10s go? Some people would leave this 10 to the n in the denominator, bring that 10 to the denominator as 10 to the minus 1, and they'd end up with 10 to the n minus 1 power as their final piece when they combine those two. But realize there's an easy alternative. Other people would leave the 10 in the numerator, would bring this one up as 10 to the minus n, so they'd have 10 to the minus n plus 1, or 1 minus n. Either way, that's the same thing. So still we could have some subtle variations in how we write it, but that's just, that's just a little bit of a preference on how you combined it, but it's still a good habit to combine. And definitely that would be one if you did this, but then you saw the book did this. I really hope that would be a quick moment where you say, oh wait, but they are the same thing. So again, you did a good job and you have a correct answer. One more like this. Number 3, still same directions, everybody. We're still going to go through the whole thing. We're going to find the power series and give the corresponding interval of convergence. So this last one, let's look at, we'll make this c of x. We'll go 12x to the 5th power over, let's go 4 plus x. And this just kind of combines aspects. Ooh, I'm sorry, 4 plus x cubed. Sorry about that. This just combines aspects from both problems 1 and 2. Need to start here with the 4. Take the 4 out, 1 plus x cubed over 4. And then, this doesn't have to cancel, but that's just a nice thing to realize. Here the 4 cancels with the 12, you have a 3 left over. This, still not perfect. 1 plus this needs to be 1 minus my r value, and that is now r. So I've got 3x to the 5th as my a value times minus x cubed over 4 as my r, a r to the n, and that once again starts with n equals 0. And once again, good answer, but we could clean it up a little bit. Few things here. The 3 is not going to combine with anything, but that's still there. This will become a minus 1 to a power. I'll end up getting x to the 3n power when I distribute the exponent there. And an x to the 5th will become x to the 3n plus 5. The denominator, you get a 4 to the n. You know, we saw in the previous, we had 10s and 10s. Good idea to combine them when you can. 3s and 4s are not going to combine. One little thing I should have done. Most of the time, the book kind of likes to keep the x term by itself, and then we'll keep all these lumped together. They might, because they're both a perfect n exponent, they might combine that to minus 1/4 to the n, but I think that's less likely. I think they'd probably leave it separated like that. So there's a good power series, perfectly good answer. And there we've just cleaned it up a little bit. And this points out that, again, our perfect power series, well, our initial power series goes again that c sub 0 plus c sub 1x to the first power plus c sub 2x to the second power. So it almost seems like it has to be an x to a perfect n. But now through a couple of these, we had x to the n plus 3, x to the 3n plus 5. So it still has x to a power, and that still completely satisfies it being a power series. Thinking about just interval of convergence, absolute value of negative x cubed over 4 has to be less than 1. The negative would drop with the absolute value. We get absolute value of x cubed is less than 4. Not pretty. I probably should have tried to make this an 8, so at least the cube root would give us a nice number. But we'll still, cube root works out well. We get negative the cube root of 4 is less than x, which is less than the cube root of 4. And that would be your interval of convergence. So hopefully, again, 11.8 was a pretty tough unit, but hopefully just seeing a few of these problems, you get to realize it's not all just going to get so much worse and so bad. For a lot of people, this is actually a pretty nice unit so far, but now we have a few things left to add in. This next idea gets brought up on page 794 in the book. And now we go back to f of x as a power series, and we'll do this generically. They do it as centered at a, so we're going to have c sub n x minus a to the n power and I just wanted to show a few terms. And the whole point of this is to discuss what happens if you have a function written as a power series. What happens to the derivative of that function and to the antiderivative of that function? And look at it. This is the second big aspect of power series. Why are power series helpful? Well, number one that we established in 11.8 was that even though they may be these ugly long infinite sums, through technology of today and through computer programming, calculators, etc., having a computer add the first 1,000 terms, the first 1,000,000 terms, that's no big deal. That's very easily programmed, so that's one way to get nice values. You use the power series, and that you could just keep adding. But now the second nice thing is look at what happens when you actually expand these terms. Remember, the c's are all just numbers. That doesn't even have an x. This is an x term, x minus a to the first power, and x. And especially if these were centered at 0, you just have x to the first, x squared, x cubed. Again, that would be if it was centered at 0. So if you had these terms, this is our ideal situation when either taking a derivative or an antiderivative. A bunch of terms separated by addition or subtraction, just based on whether c is a positive or negative value. That's how some of these could become negatives. So we'd have terms separated by addition, subtraction, And the individual terms themselves are simple x to a power. So the derivatives here, these are basically infinite polynomials. So they're so ideal. How do you take the derivative? You take the derivative one term at a time. C sub 0 has a derivative 0. Then you get C sub 1. That would push along. The derivative here is 1. Plus, here, C sub 2 would push along. Power rule, 2 out in front. X minus a to the first power. Technically a little chain rule times an extra 1. Then this one, you get 3 times C3 x minus a squared. One more, this is where I end and put dot, 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 but if you keep going, you get 4 times C4 x minus a cubed plus dot, dot, dot. So how do you take the derivative? It's not hard at all. You just take the derivative. Here I did it term by term, but look how I could have done that generically. This would be coefficient pushes along. Here, x to a power, n, that power out in front, x minus a to the n minus 1 power. But here, one tiny little thing. You still could technically start this at n equals 0. And if you plug in 0, your first term would be 0. That's what we noticed here. The derivative of c sub 0, this is just a number, you'd get a 0. Then you get a c1 and so on. But a lot of people, they drop that. This was n equals 0. So since you just get 0 in the derivative, they start at 1 instead. It's no big deal if you start at 0. It's perfectly fine. But that's just if you notice sometimes, like in the book, why do they start that next one at n equals 1? That's the reason. You still could start at n equals 0, but now you just put in an extra 0 in your term. Instead of having the 0 plus c1 and so on, why not just skip that 0 because it's not doing anything? Okay. The same thing happens with the antiderivative. Let me just give myself a little room here, just so these don't bleed together. But now if I want the antiderivative of this function, well, look at the terms. Same thing. Derivatives, antiderivatives, we like the separation by addition, so I can go through one term at a time. Antiderivative with respect to x, I get c sub 0x, plus c sub 1 would push along. Here, power rule, add 1 to the exponent, divide by that new exponent. Next one, same thing, power rule. Right here, I'm showing you the power rule right here on the x, but this is where the book often would, again, kick those out together. C1 over 2, just keep the x to a power. But it all works out the same. C3 over 4, x minus a over 4, just like we've seen with power rule. Some people, the anti of x to the n is x to the n plus 1 over n plus 1. Other people write 1 over n plus 1 times x to the n plus 1. Same thing either way. Now we don't have to play that little game with n. This is still n equals 0, then n equals 1, n equals 2, and so on. And notice, just like with the derivative, generically inside the formula I can take the derivative, get this, expand this, realize I get the same thing as if I took the derivative term by term. Same thing happens with the antiderivative. I do at the very end. This still is an indefinite integral, so I still need a plus c at the end here. And for a lot of people, because that's weird to have plus dot, 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 and then put plus c, most people move that to the front instead. So we'll get that positive c plus. And now, right here, antiderivative generically, the coefficient pushes along, add 1 to the exponent, divide by that new exponent. That is our antiderivative. And the last part, the interval of convergence, is the same. Once you know the interval of convergence for the original, the power series for the derivative will take the power series, the derivative of the power series of the original, and that works. Same thing, how do you get the power series for the antiderivative of f? we'll take the antiderivative of the power series that went with f. But the last part, interval of convergence, that never changes. Whatever interval of convergence you had for f, you'd have the same one for f prime and the same one for the antiderivative of f. With one tiny exception, the endpoint game again. You know, just like we saw up here, this was a geometric series. We knew we didn't have to test the endpoints. But once we move on, we'd have to retest those endpoints if we had them. If this only converged at its center, well, we don't have any endpoints to worry about. If this converged for all x's negative to positive infinity, well, then again, no endpoints to worry about. But for that third case, if this converged, say, from -2 to +2, well, we saw maybe it's parentheses on both the negative and +2. Maybe one's a parenthesis, one's a bracket. Well, as we move to the derivative and antiderivative, we'd have to recheck those endpoints again. Now let's take advantage of this. The book does give us a little more nice notation. I want to point that out quickly. So now all this, what this is telling me is now the derivative of a power series looking at it this way, that derivative notation out in front of a power series is equivalent to moving that notation inside the power series. Now, I'm not going to prove that because we just keep pointing it out. It's just look at what happened. If you want to take the derivative of the power series, write out the power series, and realize the nature of the power series, you get to take the derivative of each term one at a time. And the same thing happens for the antiderivative. If you have an integral of a power series, well, that's the same as having the power series and moving that integral inside on each individual term. Technically, this has the dx on the outside. Now the dx has also moved on the inside as well as our integral notation. So, again, the same equivalent. And that's hopefully what we realize from here, but just to spell it out with notation here. So now, how does that help us? Let's go back to function a of x for a quick moment. We had a of x. That was our first problem. So let's just quickly go back through that. So we already found a of x equal to 1 over 1 plus x is equivalent to the power series minus 1 to the n, x to the n. But now, let's take a look at this, and let's think, and you know, we already had the interval of convergence, but now let's use this. Let's use A to find power series for number 1. This next one will be minus 1 over the quantity 1 plus x squared. And then number 2 will be natural log of 1 plus x. Now, this is definitely not obvious right off the bat, but this is one of those places that once we see it one time, that gives us a lot of experience and guidance to try and figure it out for a different problem. So, especially that I gave you this hint. What is the connection between this function and this function? Just to give this function a letter, let's call this function d of x. D and a are clearly not the same function. Some people might be looking at this and saying, well, wait, if I expand this, you know, they're trying to use the a over 1 minus r form, but that gets really messy. Can you do it? You can. It just really, really is a big pain. You have to FOIL this out, and then you actually have to do more work to complete the square, because you end up getting 1 plus 2x plus x squared. You have to complete the square there in order to make that 1 minus a single term to a, you know, it just really, really can be a big pain. So, right, because r can only be one term. You can't have r being a spread out term. That term could be like an x minus 1, and if you expanded that, you'd have to play a little trick completing the square. You'd end up getting x plus 1 quantity squared. So that could be your r, all of this. But now you've re-upset the balance. You have to, again, that doesn't just come for free. You have to do more work to make that happen. So again, it's a little bit of a pain. So that one can work using the a over 1 minus r form, but is a really hard process. Here, there is no a over 1 minus r. So let's look beyond that. The answer is, what is the connection between d and a, and then separately function e and a? D is the derivative of a. D equals a prime. Not obvious, but now that I've shown you that, you should be able to confirm. Take the derivative of this, think of it as 1 plus x to the minus 1 power. Use your chain rule. The derivative is minus 1 this to the negative 2 power. That's exactly what I have right here. So if d is the derivative of a, let's take the derivative of its power series. And this is where I keep saying, when you go to take the derivative, some people want to write out the terms. That as they write out the terms, they get 1, they get minus x to the first, they get plus x squared, minus x cubed, plus x to the fourth, minus ... They take the derivative one term at a time. They get 0, minus 1, plus 2x, minus 3x squared, plus 4x cubed. And then they write the power series for it. I'll ignore this term. Starting here, this is not obvious, but if you're starting to try and find patterns, well, I see an alternating sign, and the plane n works. Now that I'm starting with n equals 1, that'll start me off with a negative. But then from there, trying to find patterns, well, I get this is n equals 1, n equals 2, n equals 3. I'm getting x to the n minus 1 power with an n out in front. That would be the pattern that we're seeing for these terms. We could realize it works here. When n is 1, 1 x to the 0 power still makes everything match. But realize I just could have taken the derivative generically here. Coefficient pushed along, the derivative of x to the n, and x to the n minus 1. So whichever approach you're more comfortable with, writing out the terms, taking the derivative of those terms to then try and get this general formula, or taking the derivative of the original general formula to get to here, will all get to the same place at the end. And again, there's no harm if you left that at n equals 0. That just includes that extra term, but it doesn't hurt anything. Much, much easier, but you had to make that connection. Similar here. What's the connection between log of 1 plus x and 1 over 1 plus x? The antiderivative of a would give us this, right? The antiderivative of this, maybe you want to do a u substitution just to confirm that, but this would be your answer. Well, this plus c. So we're going to have to do a little bit of work with c at the very end here, but that's the main connection. So how do I get the power series? Well, I have the c. I should, again, be consistent. The plus c should be on all these lines. I have the plus c, but I'm going to take the antiderivative of the power series. And just like I did up here, I could do it one term at a time, or I can do it generically. This time I'll do it generically first. Leave this alone. X to the n becomes x to the n plus 1 divided by n plus 1. And there's your power series. If you did it one piece at a time, the antiderivative here would be x. Then you get minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4. And if you're trying to get a good pattern here, this has to be n equals 0. So all that matches. Then n equals 1. Well, the plus, minus, that works here. N equals 0, you get x to the first. N equals 1, x squared over 2. N equals 2, x cubed over 3. Whatever n is, you're getting 1 more than that for the exponent and 1 more for that in the denominator. So, the last part, just to realize here, just the last thing to realize here, sometimes the book just rewrites this a tiny, tiny little bit. This is another spot that sometimes they like to start it with n equals 1 instead. So if n equals 1, well, now I have to play the exponent here because I need this to start with a positive. So either n minus 1 or an n plus 1. And that just makes it a little bit nicer because now if you start with n equals 1, now the n value matches the power of x and matches the denominator. So some people, again, that's just a slight alternative. And that's where, just to realize, some reasons, sometimes we just talked about, we may have the right answer, but it's just a little bit of cleanup that we may have not shown that the book did. But other times it might just be just a slight change in the index. Is this better than this? I would argue it's not, but for some people, just that the exponent is a little simpler and it's a plain n, they might prefer that just a little bit more. And this is where interval of convergence, up here, the interval was -1 to 1, and that was parentheses. The same thing happens in this one. In this one, the -1 actually works out okay. So this one, the interval of convergence, you get brackets -1 to 1. That's what I was just saying. The main interval is still the same, but we just have to be a little careful with the exponents. If you let x equal -1, those would combine -1 to the n over n. That's an alternating series that does converge. So I'm not trying to harp on that point. I'm really trying to keep the main focus here on the power series itself and how we use the geometric series formula to get this power series. And that's where the expansion was necessary, everybody. If you still left this as -x to the n, now when you take your derivative, your antiderivative, you don't just have a simple x to a power. You've got some basic inner-outer mess. There's some chain rule going on. But as soon as you simplify it by expanding it right here, now that's just an extra multiplier. And whether it's the derivative or the antiderivative, that coefficient just gets pushed along. So that's the second advantage. So it's not just matching your answer in the book. It's if you ever had to use that power series for anything else. That's the second advantage of breaking these apart. Any derivative, antiderivative, now you've got a plain x sitting all by itself, so whatever else you have here, that just automatically pushes along. So, not trivial, but not terrible. 11.8 definitely started with some rough topics, a lot to get used to, and just getting the intervals of convergence. You know, for some people, they pick up on that pretty quickly, but for a lot of others, they need some practice. They need to see all the 3 different cases to kind of have those expectations. Here I got 0 is less than 1. All that always converges. Here I got infinity is greater than 1. Well, that never converges. But that's not a possible answer. So just making those connections takes some time. In 11.9, a lot of people get off to a very good start here, but then make sure when you get towards the end of the homework, they're not always quite this clear. They want you to think a little bit more. So we're going to do one more. We're going to finish this video with one more. We are going to find the power series for the function inverse tan x. Oh, I'm sorry, there's one other thing I need to point out here. The c. We can do a little bit of work to find c, and it's just being clever. So right here on this stage, whether you've got this is your function, And whether it equals this or it equals this, we could be clever with our choice of x. I could solve for c by picking a value for x that we know the value here, and hopefully it'll be something nice over here. And in this first one, it's really nice if we just let x be 0. If x is 0, we get log of 1 on this side, and reminder, log of 1 equals 0, equals c plus this summation, but where x is always 0. So look at these expansions. If x is always 0, we got 0 equals c plus 0 plus 0 plus 0 plus 0, and all that boils down, not always, but in this case, we get very luckily that c just equals 0. So that's why we can break that down. We didn't know that right off the bat. We had to leave the c there, but after we had our power series, we can actually find out what c is. Now, just quickly realize, if we say had to let x equal 1, over here we'd have all these terms with x is 1. We wouldn't just know that quick sum, but that sum would be the value for c. And once again, that may seem strange, but that's fine. Because once again, if you ever really needed, well, a better value, what is that c? Let the computer figure out what that sum actually is. Okay, so now, last problem. How on earth are we going to find the power series for inverse tan? Well, it's a little similar to what we noticed here. Log of 1 plus x was not obvious until we realized, hey, the derivative of log of 1 plus x is this. We could find the power series for this, and then the antiderivative takes us back to where we were. Same thing happens here. Let's think about the derivative of inverse tan. And we know that. We've known that for a while. That, just a quick manipulation, can be written as a over 1 minus r. So I get a 1 r to the n, which I'm going to clean up. Interval of convergence, again, there's your r, absolute value less than 1. You'd get your interval. This time you wouldn't get the bracket like we did here, but you get a clean interval, -1 to 1. But still focusing on the power series. There is a good power series. So the derivative took me from here to here. The antiderivative will take me back from here to here. So the power series for inverse tangent will be the integral of this power series. But let me again clean that up. There's a good power series, and that's fine. But if I'm going to take the antiderivative, let me do myself the favor of cleaning that up. -1 x squared to the n is -1 to the n, then x squared to the n, which is x to the 2n. Now I can take the antiderivative. I'd get my generic c. Actually, I shouldn't have put my c here, right? The c comes after you take the antiderivative. But after we took that antiderivative, we had that extra plus c. And that's where that antiderivative, we had the c here, also here, until we found c was 0. But that's just my little mistake, everybody, right? The c comes after we take the anti, not while we have that notation. But now I am taking that antiderivative. This pushes along. The anti of x to the 2n is x to the 2n plus 1 divided by 2n plus 1. And if we want to find c, same thing that we did before. And it works out exactly the same. If I let x equal 0, inverse tan of 0 is 0, c plus all of this when this term is 0. This whole thing goes to 0, so c equals 0, and we can finish. Inverse tan has this as its power series. So all the problems in 11.9, if you know what you're looking for, they can go pretty fast. If you know you have that geometric series form or just have that little manipulation to get there, that should be pretty quick. And then for some of the harder ones, when you recognize, oh, hey, this is the derivative of something that is that form, let me get that form and take the derivative to get the new power series. This, again, the derivative of this gives me this, so the antiderivative will give me the power series for this. The derivative of this gives me this nice geometric series form. There's the power series. So the antiderivative of that power series gives me this new power series. The work itself, getting the power series, taking these derivatives, taking these antis, I'm not saying they're easy. They sometimes just take a little bit of practice, but they're not that bad. We've done much, much harder things. And as I keep showing you, I keep taking the derivatives and antis, and I've showed you both ways. I showed you up here the derivative term by term, and then get the power series that goes with those terms. The antiderivative term by term, and then the power series that would go with all those individual terms. Here I just did it generically, but again, no problem. Do it term by term if you like. This goes 1 minus x squared plus x to the 4th minus x to the 6th plus dot, dot, dot. So the antiderivative would then be x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7 plus dot, dot, dot. And that takes a little work to see, well, when n equals 0, I need 2n plus 1. But as you get later on, look at the exponents. You keep increasing the exponent by 2. Hence, you needed a 2 times n. But the plus 1 made everything balanced. Once you figured out the pattern in the exponents, notice the denominator are the exact same terms. So there's a lot of little things that some people do that are different as far as getting these exact series. But make sure you realize what it is that you need to do. That's, of course, the first and foremost part.